So here in this problem, we are provided with the quadratic equation x squared minus 2x plus 4 equals to 0, which have got two roots given by alpha and beta. We need to show that the following expression is true. So let's begin. So we'll start with our given equation. So here we have our equation given by x squared minus 2x plus 4 equals to 0. So we'll need to find out the two roots of this given equation. So here we can use the standard quadratic formula. So x will be equals to, we have negative of b, so b here is negative 2, plus or minus square root of, so we need b squared, which will be negative 2 squared, minus 4 times a, which is coefficient of x squared, multiplied to c, which is the constant, whole divided by 2 times the coefficient of x squared, so that's 1. That will be equals to 2 plus or minus square root of, so square negative 2 squared, that will be 4, minus 4 times 4, that's 16, whole divided by 2, which gives us the value 2 plus or minus, we will have negative 12 divided by 2. Now we know that I squared, or the iota squared, that's equals to negative 1, so we'll have 2 plus or minus square root of 12 iota squared divided by 2, which is going to give us 2 plus or minus 2 times I multiplied to square root of 3 whole divided by 2. Or simply put, we have 1 plus or minus, we're dividing both terms in the numerator with 2, so we have 1 plus iota times square root of 3. So this is x, so we have obtained two roots. So one of the roots is, let's say alpha is given by 1 plus iota times square root of 3, and the other one, let it be beta, so beta is equals to 1 minus iota times square root of 3. So now that we have obtained the value of alpha and beta, our next goal will be to convert alpha and beta to polar form. So we'll start with alpha equals to 1 plus iota times square root of 3. So here r will be given by, so we have square root of 1 squared plus square root of 3 whole squared. So this is going to give us a value 2, and we need to find out the argument of alpha. Here alpha is a complex number, so its argument will be the inverse tangent of the imaginary part divided by the real part. So this is tangent inverse of square root of 3, and we know that tangent of pi over 3, that value has a square root of 3, so that means this will be equals to pi over 3. So we have obtained the argument as well, hence we can express our alpha as equals to 2 multiplied to cosine of pi over 3 plus iota times sine pi over 3. Right, now we'll move on to beta. So our beta is given by 1 minus iota times negative square root of 3. So here r will be equals to, we have 1 squared plus negative square root of 3 whole squared, which will be equals to 2. And argument of the complex number beta, that will be equals to the inverse tangent or the arc tangent of the imaginary part, which is square root of negative 3 divided by the real part, which is 1. So this will be equals to tangent inverse of negative of tangent of pi over 3. But we know that tangent is an odd function. Since it's an odd function, we can rewrite negative of tangent of pi over 3 as tangent of negative pi over 3. So tangent inverse of the tangent function is simply going to give us negative pi over 3. So that means our beta, now we'll express beta in the polar form. So beta can be expressed as 2 times cosine of negative pi over 3 plus iota times sine of negative pi over 3. Fine. Now cosine is an even function, so that means we have 2 times cosine of positive pi over 3 minus sine is an odd function, so we have negative iota times sine pi over 3. So we have obtained the value of alpha. Alpha came out to be 2 times cosine of pi over 3 plus iota times sine of pi over 3. Now we will find out alpha whole raised to the power of n. So this will be equals to 2 raised to the power of n multiplied to cosine of pi over 3 plus iota times sine of pi over 3 whole raised to the power of n. So that means we can use the De Moivre's theorem, which is simply going to give us the value cosine of n pi over 3 plus iota times sine of n pi over 3. Similarly, if we find out beta raised to the power of n, so that means we will have 2 raised to the power of n whole multiplied to cosine of n pi over 3. So here we'll have negative iota times sine of n pi over 3. Now we will finally add the value of alpha raised to the power of n and beta raised to the power of n. So if alpha raised to the power of n added to beta raised to the power of n, so that gives us the value. So here 2 raised to the power of n, that's a common factor. So 2 raised to the power of n, and we'll see that the imaginary part will get cancelled out, and that leaves us with only the real part. Now the real part is repeating twice, so we have 2 times cosine of n pi over 3. So 2 raised to the power of n times 2, so this will get multiplied, and this is going to finally give us alpha raised to the power of n plus beta raised to the power of n. This will be equals to 2 raised to the power of n plus 1 multiplied to cosine of n pi over 3. So this is what we were asked to show, hence proved.